battleground. Tomorrow, next year, 10 years. Raw power. For modern warfare means power. Many kinds of power. Highly mobile, readily available, effective power. Manpower. Ready to protect freedom anywhere in the world. Firepower. Mobile, fast, effective. Electronic power. A new concept in combat operations. Nuclear power. Rugged, mobile, quickly available, supplying electric power without the aid of conventional logistics. Today, our highly mechanized armed forces, committed to action anywhere on Earth, depend heavily on electric power. Power which can be supplied for long periods in remote or hard-to-reach areas. Power for radar installations, which may be stationed at the outposts of the world. Power for field hospitals, enabling the use of advanced scientific instruments and newer lightweight hospital equipment. Power for research and exploration in areas cut off from practical supply lines by weather and distance. Power for disaster areas, areas which may be isolated from normal supplies or hazardous to continued delivery. Power for forward air operations, which would allow tactical use of all available fuel. Power for port facilities at temporary, expedient locations. Power for modern command headquarters using electronic computers and plotting equipment. Power. Electric power, mobile, dependable, self-contained, and capable of all-weather field operation for $50,000. Several years ago, the Army recognized the growing need for such a power system. Existing generating systems using fossil fuel heaters could produce the necessary 300 to 500 kilowatts of electricity. But they created the logistics problem of having to supply 900 gallons of oil a day. That would amount to about 350,000 gallons a year. For remote site operation, this, of course, was unacceptable. A system was needed which could provide power for more than a year without the constant problem of refueling. In addition, the plant must be transportable by Air Force cargo plane, or by ship, or rail, or primarily by Army semi-trailer. It must be capable of remote site operation within 12 hours of arrival and capable of relocation within 24 hours after shutdown. A nuclear power package was the logical system to meet these requirements. Jointly, the Atomic Energy Commission and the Army Corps of Engineers began a program to develop such a system, which was to be designated ML-1 for mobile, low-power, first prototype. The ML-1 principle of operation was to be based on a modified Brayton system. Now, this is a closed-cycle gas flow system in which heated gas is employed to drive the turbine compressor. However, when we set about developing this system to meet the nuclear power requirements, we ran into a number of unique problems. For instance, a conventional system uses air as the circulating gas. Early investigation indicated that nitrogen would be less corrosive than air for long-time operation, although air may be eventually used for logistics reasons. A molecule of gas makes a complete circuit in about 1 second. This gas, as in a conventional system, circulates to drive the turbine, going in as a hot, high-pressure gas on one side, giving up its energy to drive the turbine, and coming out cooler and at a lower pressure. Unlike ordinary turbines, however, this one has to be light in weight and still be capable of operating for thousands of hours without breakdown and without lubrication leaks that could foul the system. The gearbox reduces the turbine's revolutions per minute by a ratio of 5 to 1, and this lower speed is used to drive the brushless generator, which is called an alternator. For the power it delivers, this alternator is smaller in size and weight than previously believed possible. After leaving the turbine, the gas, which is still extremely hot, passes to a recuperator. This recuperator does a remarkable job of transferring several hundred degrees of this excess heat to a cooler gas in approximately 0.08 of a second. The gas is cooled even more in a pre-cooler. This additional cooling lowers the gas temperature prior to entering the compressor section of the turbine compressor set. Warm compressed gas is then run through the cold side of the recuperator, where it picks up the excess heat from the hot side of the gas cycle. In passing down through the reactor, the gas has approximately 1/50th of a second to pick up the additional heat it needs to run the turbine. This system has a net output of from 300 to 500 kilowatts of useful electric energy. Development of the system was accomplished by dividing the power plant into two separate packages mounted on individual skids, the reactor skid and the power conversion skid. The reactor was developed by the Atomic Energy Commission through its contractor, Aerojet General Corporation. Basically, it is a high-temperature, gas-cooled, water-moderated reactor producing 3 megawatts of thermal energy. Development of the unique ML-1 reactor was complicated by several factors. For instance, it had to be about half the size and weight of other reactors of equal power. Then, too, little was known about closed-cycle gas-cooled operation at high temperatures. Because the development of the mobile reactor was so complex, a special gas-cooled reactor experimental facility was constructed at the Atomic Energy Commission's National Reactor Testing Station in Idaho. Designed and operated by Aerojet General Nucleonics, the GCRE facility houses an experimental reactor which employs the ML-1 principle of operation. 20 feet of water shields the entire reactor assembly so that it can be safely observed during research operations. Also, the control rods are brought into the reactor from the side, much as they will be in the ML-1. The primary purpose of the GCRE was to demonstrate the feasibility of the closed-cycle gas-cooled reactor principle. This was accomplished in February of 1960, when criticality was attained. Since that time, the reactor has logged over 2,200 megawatt hours of operation. The second purpose of the reactor was to test reactor components for the ML-1 system and for future, more advanced systems. The original GCRE experimental fuel elements were constructed of uranium oxide clad with stainless steel. The sandwich was rolled into long, flat plates, which were later curved. After a number of processes, such as stress relief in a high-temperature retort, the plates were assembled into experimental fuel elements. The first GCRE research core was made up of these cylindrical fuel elements. Their successful operation proved the concept. However, a series of experiments proved that the size of the reactor could be reduced further by using pin-type elements. Consequently, Aerojet Nucleonics designed and fabricated a number of the pin-type elements. Essentially, the elements consist of urania and urania beryllia pellets, which were highly enriched with U-235. The pellets are loaded into slender tubes or pins made of Hastelloy X, a metal which can withstand extremely high temperatures. 19 of the pins are bundled to form one fuel element. Because reactor heat is produced by fissioning of uranium, placement of the pins in the bundle is critical. Arrangement of the pins is carefully worked out to ensure an even temperature distribution within the element. The bundle of pins is inserted into a double-walled tube which contains fibrous insulation between the tube walls. This thin insulation barrier helps contain the fission heat inside the tube where the gas can carry it away, and at the same time prevents boiling of moderator water which is in contact with the outside of the pressure tube. Although it appears simple, The complete fuel element is the end result of several years of reactor research, including months of specialized experimentation in the ML-1 program. As an engineer of Aerojet Nucleonics puts it,
this GCRE facility was designed specifically to provide research information for a closed-cycle, gas-cooled reactor. The subsequent knowledge generated here helped us to build the small portable reactor for the ML-1 plant. This doesn't mean that our work here is finished, however, because the GCRE facility can continue to give increased knowledge of gas-cooled nuclear reactor systems.
Just as the GCRE facility was constructed for reactor research, so too, research on compact power conversion equipment is being conducted in the gas turbine test facility called GTTF, which is located at the Army Engineer Research and Development Laboratory, Fort Belvoir, Virginia. The GTTF contains an experimental, closed-cycle, gas-driven power conversion system. For these tests, no attempt was made to achieve the same degree of compactness so necessary for the mobile package. The individual components are not identical with those that are used in the ML-1. However, the principle of operation is the same. A high-temperature, kerosene-fired heater is used in place of the reactor to supply heat for this system. To obtain the necessary 1,200 degrees of operational heat, the furnace uses 50 gallons of oil per hour. If the heater could be continuously operated for the entire ML-1 life of 50,000 hours, it would use 2,500,000 gallons of fuel. While development of the power conversion system may seem simple in comparison to reactor development, this is far from true. Although based on known principles, the lightweight, the ruggedness, the compactness, and efficiency required for the conversion system have made it necessary to develop new applications for old principles. Then, too, the individual components are being subjected to operational demands never before required. As one sergeant said,
"Sure, we've had our problems, but that figures when you stop to think that this turbine alone has to rotate at 18,000 RPM and run more than a year without maintenance. When we finish the system, we'll turn out better than 300 kilowatts.
The results of these tests were of great value to the ML-1 program, especially in the area of thermodynamics data and information on control of the closed-cycle plants of this size. Fort Belvoir is also the location of the Army Nuclear Power Program Training School for nuclear power plant operators and technicians. Here, the first half of a rugged 2-year training program is accomplished. Previous classes have shown that men trained for work on nuclear electric power systems do not require exceptional educational backgrounds. These men are mostly high school graduate level, although they are carefully selected for intelligence and ability. General training begins with an intensive 16-week academic phase. Part 1 of this course includes mathematics, physics, nuclear engineering, electrical engineering, mechanical engineering, health physics, and plant information. Next, trainees are instructed in specific plant operation for another 16 weeks. During this and succeeding phases, training is conducted in small groups, which allow individual attention. In the case of the ML-1, each member of the crew must be capable of operating the system. Each crew member then completes his first year's training with a separate specialty course. The ML plants, for example, will have an operator mechanic, an operator electrician, an operator instrument man, and a process control operator. The process control operator is also a trained health physics specialist for radiological safety. His training primarily concerns allowable radiation dosage levels for military personnel as prescribed by the Army Surgeon General. The specialist learns that the ML-1 power plant presents no radiation problems when proper operational procedures are followed. It is his duty to see that they are. During their second year, the trainees participate in actual operation of the reactor and its power conversion system. The information obtained from the two test facilities, the GTTF and the GCRE, enabled construction to go ahead on the ML-1 prototype. Fabrication of the nuclear package was accomplished at Aerojet General's Downey, California division. The heart of the package is the reactor core with its 61 pressure tubes. When the reactor is ready for operation, the pin-type fuel elements are inserted in these tubes. The core is contained within an inner tank of stainless steel. This tank is lined on the inside by a circle of lead and tungsten which act as neutron reflectors. The outside of the tank supports a shielding layer of lead and boron. Gussets attached to the reactor hold it suspended inside a large metal tank. Before operation, this outer tank is filled with borated water, which completes the shielding necessary for reactor operation. Manufacturing tolerances for the ML-1 reactor are much more critical than those required for other reactors, due in part to the problem of containing high-temperature nitrogen gas under pressure. In addition, the assembly has to be rugged enough to withstand transportation shocks and vibrations while still keeping within weight limitations. Many of the same problems were encountered in the design and manufacture of the power conversion package, which was accomplished at Aerojet General's Azusa plant. Here, too, compactness and weight were critical, as was the ruggedness necessary for transport. After fabrication was completed, the package was connected to an oil furnace and operationally checked. Of primary importance during the series of test runs was checking of the operational controls which automatically regulate the system in response to fluctuating electrical loads. In addition to the primary components, numerous operational subsystems are also included on the power conversion skid, such as the lubrication system, the nitrogen oil reclaiming system, the cooling system for the moderator water, circuit breakers, protection relays, surge conductors, transformers, and lightning arresters.
Actually, this package is a miniature Hoover Dam, except that we have a dual capability, because we're not only producing electricity, but that there's enough high-temperature air coming off of that cooler there to heat more than 70 full-size homes.
Design and construction of the control cab also presented unique problems. Here, too, weight, compactness, and ruggedness were the important factors. These requirements were met by using transistors and sealed relays in the instrumentation and control circuitry. The operational controls were also unique for their fail-safe simplicity and for the fact that, for the first time, a reactor of ML-1 size could be operated by one man if the situation required. When complete, the entire control system is capable of transport and operation mounted on the bed of a standard M35 2.5-ton truck. Design and fabrication of operational auxiliary equipment also had to meet mobility requirements. Separate skids are utilized to mount the gas storage unit and the cable reels of the control cab. Shock tests using mock-ups of the reactor and power conversion packages were carried out to test transportability. Loaded onto railroad flat cars, the mock-ups repeatedly withstood heavy collisions with other cars. Although the shock loads were deliberately high, all high-amplitude shocks and vibrations were effectively absorbed. When fabrication and testing of the individual packages had been accomplished, the complete ML-1 plant was assembled in a specially constructed testing facility in Idaho. For the first time, the reactor and the power conversion skids were joined together. The pre-start checks were made, gas was circulated through the plant, and the reactor was brought to criticality. After preliminary low-power operation, the system was successfully brought to full power. Now the ML-1 was ready for the field. We loaded it on standard Army carriers and took it to a remote location. The site was selected for its natural shielding barrier, although a similar pile of earth could have been thrown up by a bulldozer. In this case, we left the plant mounted on its trailer, but for long-time operation, it could be positioned on the ground. While the auxiliary startup and operational skids were being unloaded, the health physics member of the crew roped off a 500-foot radius. Warnings were posted to keep personnel out of the radiation area during reactor operation. While the control and instrumentation cables were being coupled to the control cab, we started the auxiliary generator to provide system startup power. With operating power established, we initiated communications between the control cab and the other crew members.
This is control.
How do you read me?
I read you, Sergeant. Switch on the moderator pump.
Yes, sir. Moderator water pump coming on.
We pumped the moderator water through the demineralizer and into the reactor core. We then pumped shielding water into a collapsible tank. We mixed boric acid with the purified water and then pumped it into the reactor tank, where it acts as an operation neutron shield. Following gas loop pressurization, we made a pre-operational check of the entire system.
Starting channel 2. A, valve position.
A short time later, after all personnel had cleared the area, we brought the reactor to criticality and slowly brought the system to full power, no load condition. Approximately 12 hours after on-site arrival, the plant was in full operation, and we switched the current on the line. While the ML-1 plant is not the answer to all mobile power requirements, it does fulfill certain critical needs. It is our belief that the nation's defense posture is constantly being strengthened by the intelligent use of nuclear power. This nuclear plant is designed to deliver power safely in areas where logistics problems prevent the use of more conventional equipment. We realize that it isn't cheap, but we also know that for long-time operations in remote areas where it may be difficult to maintain supply lines, or in many military operations impossible, that in these instances, the break-even point with other systems is quickly reached and passed. The fact that this plant can be transported by every means of common carrier, and the fact that it can deliver 300 kilowatts of electricity for approximately a year without refueling, makes it an extremely valuable contribution to our defense effort. Operation of the prototype plant does not mean that all developmental work has ended. As new advancements are made, the size and weight of the package can be reduced, while at the same time increasing the power output. And someday, power reactors will help us conserve our fossil fuels. The problem of air pollution from conventional power plants can become a thing of the past. Isolated industries will be given the continuous power they need to conduct operations in any locale, any weather. And underdeveloped communities throughout the free world will someday be brought nearer the standards of their neighbors through the use of economic nuclear power.